Welcome to Homework Lib.
In this question, we are told that there are 4 possible ester molecules that can form from the molecular formula C4H8O2. And we are asked how we can distinguish between these esters using their proton NMR spectrum. So we can go through the ester structures and see what their NMR spectrum looks like. And point out differences between the spectra. So one of the esters that would be likely to form with that molecular formula would look like this. And it will have 3 types of protons. So this tells us that there's going to be 3 signals in this spectrum. And then if we try to figure out the splitting of each signal, so the C protons will give rise to a singlet because they don't have any neighbors that have protons. And then the B protons will give rise to a quartet because of the 3 methyl protons plus 1 are going to be equal to 4. And then the A protons will give rise to a triplet from the 2 B protons. And we can tell that the most downfield out of these protons is going to be the C proton, which is adjacent to this oxygen. So the most downfield signal is going to be a singlet corresponding to C protons in the first molecule. And then we will have a quartet and then a triplet. So if we move on to the next ester, we can draw a structure that looks like this. So there can be a ethyl group after the oxygen. This will also have 3 types of protons. But the splitting will be different in this case. So in this case, the C protons will split into a triplet because of the 2 B neighbors, and then the B protons will split into a quartet, and then the A protons, the signal for it will split into a singlet because there's no hydrogens on this adjacent carbon. So we have again a singlet, a quartet, and a triplet, but their relative positions will be different. So in this case, the quartet is going to be the most downfield signal because that is adjacent to the oxygen. So the proton adjacent to the oxygen, or the 2 protons from B that are adjacent to the oxygen, will give rise to the quartet, and they'll be the most downfield. And then it will be the singlet corresponding to the A protons. And then finally it will be the triplet corresponding to C protons. And one of the other possible structures is this. So because we have a propyl group, once we construct the ester group, propyl can have, the propyl group can have linear and branched configurations, and that's why we will have 2 more types of esters. So in this case, this single proton will give rise to a signal, write them in red like I've been doing, and then this will give rise to another signal. These 2 methyl proton pairs will give rise to another signal. So again we have 3 signals, but this is going to be giving rise to a singlet because there are no neighboring protons. Like on this oxygen we don't see any protons. And B protons will give rise to 3 plus 3 plus 1, a septet. And then the C protons will give rise to a doublet. So this time the signals are going to be extremely downfilled singlet coming from A protons. That will be near 9 and 10 ppm. And then the B protons will give rise to a septet. And then we will get a doublet from the C protons. So I'm not even discussing the integrations here because we can use the most downfield peak and the nature of that downfield peak to identify between these esters. But yeah, looking at the integrations and again looking at the relative positions of those peaks corresponding to these integrations will also tell us which NMR spectrum corresponds to which ester. And then we have one last ester to look at. Like I said before, this will just be an ester that has a linear propyl group. We looked at the branched propyl group before, and now we can have the linear version. So again, this will give us to a unique signal. And this and this will give rise to separate signals. So this is the only ester that's going to give rise to 4 signals. So it should be easily distinguishable from the others. And let's also look at the multiplicities of these peaks. So the peak A will be a singlet due to the lack of neighboring protons. B will be a triplet from splitting by the C protons. And C would be a multiplet because of the splitting from both B and D protons. And then the D protons will give rise to another triplet because of the 2 C protons. So again, the most downfield signal in this case is going to be a singlet corresponding to A protons. And then we will have a triplet corresponding to B protons. Then we'll have a multiplet for C protons. I call it a multiplet because we don't know how much overlap there will be between the peaks. And then finally we will see a triplet corresponding to the D protons. So the final 2 esters that we looked at have singlets as their most downfield signal, but the final ester has 4 signals instead of 3, so we can distinguish between the latter 2 esters. And the first ester is going to be different from that because of its quartet and triplet that follows, which is not the case for this ester. So we can use the positions of these peaks and the order of the peaks, like where we see the multiplicity, what comes next, and the arrangement of these peaks to distinguish between these 4 types of esters that have the molecular formula C4H8O2.